In this video, we're going to look at something called standard conditions of temperature and pressure. Sometimes chemists want to be able to calculate things about gases or substances where we have something as a comparison to always compare against. And typically we call these standards. And so for gases, there are two particular type of characteristics that we use as standard conditions, and that's temperature and pressure. So what are these standard temperature and pressure of gases? By the way, we use STP as an abbreviation of that phrase. And the standard temperature for a gas is 273.15 Kelvin or 0 degrees Celsius. And sea level, or 1 atm, is the standard pressure. And depending on which particular unit you like to use, that might be a different equivalent value. So if you wanted to kilopascals, this would be 101.325 kilopascals. Now, this particular set of information is important when we do lots of calculations and comparisons to how gases behave in other particular pressures and temperatures, and we'll use this standard temperature pressure later on. The other thing that we can determine about a gas is something called the standard molar volume. And the standard molar volume is actually a specific volume, the volume being 22.4 liters, if you are at STP, which means standard temperature pressure, the temperature of 0 degrees Celsius and 1 atmosphere, and you have 1 mole of that gas. And obviously these gases must act in an ideal behavior. But also, the really interesting thing about this is that it does not matter what gas it is. Every gas at STP and 1 mole has a volume of 22.4 liters. I wanted to show you this calculating using the ideal gas law. And so if we plug in all the values for standard temperature, pressure, and 1 mole, I bet we calculate 22.4 liters. So I'm going to solve for volume here, put in our T over P, and then we're going to plug in all these standard values. So 1 mole, since let's calculate this pressure in ATM. So that's use 0.08206 liters ATMs per mole Kelvin for our R. And our temperature is 273 Kelvin. And our pressure of 1 ATM. And if you plug this into your calculator, guess what? You get 22.4 liters. And nowhere in here did I indicate anything about what kind of gas it is. It's because it doesn't matter. All gases at 1 mole amount using standard temperature and pressure have approximately 22.4 liters in volume. And you can kind of see this in these balloons down here. This is a mole of helium gas, a mole of ammonia gas, and a mole of oxygen gas, all weighing in mass different amounts, but all being 1 mole in calculation, all have the exact same volume, no matter the size of the molecule of that particular gas. And so that would be the 22.4 liters. So let's use this information to help us solve an example problem. So it says a cylinder of medical oxygen has a volume of 35.4 liters and contains oxygen at a pressure of 151 atms and a temperature of 25 degrees C. And so again, we have that 35.4 liters. What volume of oxygen does this correspond to at STP conditions? So we're moving conditions, guys. We're changing what the temperature and pressure are from the original condition 1. So this is condition 1, and this is condition number 2. So anytime you know that you have changes in the variables or values of a gas from one situation to the next, that's going to be one of the Montan, Avogadro, Boyle's, or Charles law. And again, in previous videos, I've said that if you just use the combined gas law, you don't have to choose between the four other versions of that conditional changing gas laws. So let's use the combined gas law, which looks like this, where we have condition 1 on the left, condition 2 on the right. And let's write down the information we have. We know P1, V1, T1, and N1, P2, V2, T2, and N2. And let's see what we got. So P1 is 151 ATM, V1's 35.4 liters, T1 25 degrees C or 298 Kelvin. And we don't have an N1, so let's just kind of hold off for that for right now. What about P2? We do know what P2 because it's a standard pressure. That standard pressure is 1 ATM. V2, that's what we're trying to solve for, and so we're unknown on that. T2 is that second standard temperature. We know that's 0 degrees C or 273 Kelvin. And we were told nothing about the amount of the gas. And if you'll notice, it just we didn't change the amount. It never says in the problem that we changed the amount, so we actually technically don't need N2 and N1. So let's just go ahead and cut those out. And so now what we can do is we've gotten all the variables determined except for V2, and so that's just what we're going to solve for. So I'm going to go ahead and plug these values in. I have 151 ATMs for P1, 35.4 liters for V1, 298 for T1. P2 is 1 ATM, B2 unknown, and T2 is 273, Kelvin for the second temperature. And we're going to solve for V2 by multiplying by the reciprocal of this information here. So 273 Kelvin by 1 ATM on both sides. And they cancel over here. ATMs cancel, Kelvin cancels, leaves you with volume, and that's what we are wanting to do. So I get on my calculator, get something of 4,896.9 liters, and we want to make sure that we write this in the appropriate significant digits. And let's go ahead and consider the values of standard temperature and pressure as exact values. So we won't use 1 as our 1 sig fig. Let's just go ahead with 3 significant digits. And so that means we're going to cut off here and use this value to round up. And that ends up giving us something like this, but that ends up being 2 significant digits. So what I'm going to do is I'm going to move this decimal 3 times to the left, make this 4.90 times 10 to the third liters. And that will give me a value that's equivalent to this, but in 3 significant digits. So this is how you use standard temperature pressure. It's nothing other than a set value for temperature and pressure of 1 atm and temperature of 0 degrees C.